I don't officially study it. I'm not part of. Oh, cool! Great. It's recording. Okay. I don't officially study constructor theory. I'm not part of the research lab that studies it, but I've been studying it independently for 2 years and I found it really interesting. And I'm just going to explain the problems that constructor theory solves, or I'm going to explain some problems with the prevailing conception of fundamental physics. I'll first lay out what the prevailing conception is, then I'll show that, then I'll give examples of problems in physics, and then I'll show how constructor theory is a different mode of explanation than the prevailing conception, and I'll show how it solves those problems, and then we'll see some of the reach of that mode of explanation into new domains like emergence and morality, as Trent mentioned, which I'm really excited about, and that's some of the stuff that I'm doing. It's not being, no papers on that have been published yet. Okay, so that's some of the more speculative parts at the end. Okay, so yeah, constructor theory is a new mode of explanation. The prevailing conception is a way of explaining physics in terms of, in certain terms. It's a way of explaining physics in terms of initial conditions and laws of motion. So we explain states by saying, oh, there were states before this, and then the laws of motion brought them into this future state. But often in physics, and just notice that there's a little interesting note that often in physics we want to know what can be made to happen, not necessarily what will happen if sort of we don't interfere. We often want to know, how can we figure out how to avert some disaster or use some resources or access some resources, rather than trying to figure out what will happen given initial conditions. We're not trying to predict our future, we're trying to choose our future. So, and that sounds super inspiring, but this is actually like a new mode of explanation for physics. It's like mathematically interesting. So the prevailing conception, initial conditions plus laws of motion gives you final conditions, is in a one-to-one correspondence with the theory of computation. So the theory of computation, the most fundamental theorem in the theory of computation is the Church-Turing-Deutsch thesis, which states that it's possible to build. There is a physical object whose computations are in a one-to-one correspondence with all the possible physical processes that are allowed by quantum physics. So it's the thesis that in some way, the study of the universal computer contains within it all the diversity of physics. So, but in some way, and there's a flaw in the way in which it seems to contain all physics. So yeah, this correspondence between computations and physical processes sort of looks like this. In computation, we have a computer that runs a computation which takes an input and follows rules to bring about an output. And then in the prevailing conception of fundamental physics, we study physical systems, which undergo motion from an initial state according to laws of motion, and then reaches a final state. So that is the prevailing conception, and it's connected fundamentally with the theory of computation and the theory of the universal computer, which is the deep theory. And there are some problems, obviously, with current physics, and I'll just list a bunch, and then I'll show you that constructor theory actually solves all of these problems. They're all very big problems, but constructor theory actually solves all of them, and many of them are very well known. So I think on the deepest level, the universality of computation shows that there's a physical object which can simulate any other physical process described by quantum physics. That universality implies that at the level of computation is independent in some sense from the level of hardware. So, and that's because the computations can be run not only on a universal computer, but like for every computation that's run on a universal computer, it's run somewhere else in the physical world. There's a system that is described by the function, and then there's a computer that simulates the system by computing the function. You know how to do that, I hope that was it. But yeah. So it's the very universality of the universal computer that shows that there's something lacking in it, because that independence means that that theory can't describe what is different what is different between simulations of systems and the systems that are being simulated. So it ignores hardware, essentially. That's a way of understanding this flaw in the prevailing conception. Yeah, so hopefully you've read those words by now. So clear translation. David Deutsch says that the way to understand this problem with the prevailing conception is that it can't explain which computations correspond to which physical systems. So it's like, okay, we have a universal computer. We know that all the computations in its repertoire correspond to some physical system, but we don't necessarily know which computations correspond to which physical system just by knowing that theorem. And that is certainly kind of what we want to study in physics. That's most of physics. So in some sense, the universal computer contains all the diversity of physics. In some sense, it leaves out most of it. Thermodynamics is an area of physics where the problems in the prevailing conception, thermodynamics is an area with a lot of problems in physics. With big problems. Two of them being that the second law of thermodynamics is time reversal asymmetry. So laws of motion don't distinguish between the direction in time that they apply to. If a forward evolution of a physical system is allowed under laws of motion, then its backward evolution is not precluded by those laws of motion. The laws of motion don't rule out the backward evolution of that. But in physical reality, we see that it's hard to break a glass, or it's easy to break a glass, but it's hard to put it back together. There isn't that symmetry that we see in the time symmetry of laws of motion. The second law of thermodynamics is a law that explains all processes of that kind, like breaking glass and putting it back together, making toast, untoasting bread. It's funny because it never happens in physical reality, I guess. If we lived in a universe where it did happen, I guess we wouldn't be laughing. It would be a fun thing. But thermodynamics, that's one main problem with thermodynamics that many physicists know about. Another problem is that conservation laws stated in the prevailing conception are stated weakly and misleadingly. They don't rule out, the statements of them in the prevailing conception they go like this. there's a quantity defined on an isolated system which doesn't change. But isolated systems have many unchanging variables. Like if a system's isolated, if you have a crystal that's an isolated system, then its crystal structure doesn't change. Its temperature, that's clearly thermodynamic. Many things about isolated systems don't change. It's not the fact that some variable will not change that is actually the regularity that conservation laws should express, can express, and should. The regularity is actually that any system can't have its energy be changed. The energy of any system can't be caused to change reliably and accurately. That's a summary of the solution, which I'll get to later. But that's another problem with thermodynamics. Probability is it's an area of physics, which is kind of a controversial statement, but probability is about outcomes of measurements, and measurements are, the theory of measurement is irretrievably within physics. So that's an argument for why probability is within physics. Problems in the theory of probability are glaring. Frequentism is wrong because it refers to infinite sequences of experiments, which are not real. They don't happen in reality. So no statement in the frequentist theory of probability can ever imply any fact about any physical situation. Bayesianism has the problem that it's the problem called the Duhem-Quine thesis, but that thesis is not usually it's not usually thought to problematize Bayesianism. Bayesianism is the theory that all our ideas and theories about the world obey the probability calculus. So when people say general relativity is probably true, Bayesianism is saying that's a formal statement, formalizable, makes sense. But it has the problem that, and that evidence works by updating probabilities according to Bayes' rule. So that's problematic because evidence actually works in a way that we have to creatively respond to. When an experiment fails to meet our expectations, we don't know whether or not it's the theory that we're testing or one of the background assumptions that are informing our theory of the measurement apparatus and the preparation of the experiment. We don't know which of those things are responsible for the failure of the expectation to be met. Therefore, no unmet expectation, no falsification, no failed experiment, no theory that fails a test. That no such failure ever implies a different credence for a theory. It could imply, logically, that one of the background assumptions was problematic, not the theory being tested. So it doesn't imply anything about the theory being tested. So that's a problem for Bayesianism, because Bayesianism says that unmet results of experiments should be taken into account by following the logical implications of them for one's priors and updating them according to Bayes' rule. So that's a problem for Bayesianism. Those are the two main theories of probability. So probability also comes up when you're talking about quantum mechanics. And the Born rule is a formalization of the idea that that quantum systems, when measured, have probabilities, that their different possible results are described by probabilities, but they're not because of interference. Interference makes it such that the numbers that one assigns to physical systems when measuring them and explaining the relative frequencies of outcomes of measurements. Those values aren't additive, as the axioms of probability require probabilities to be. Probabilities must be additive by the axioms that define them. So, 3 problems with probability. Okay, so constructor theory solves all of these problems and more, but these problems are huge. So this is the main distinction between the prevailing conception, which is responsible for all the problems that I was talking about, and constructor theory. The prevailing conception talks about what will happen, and constructor theory talks about what can be caused to happen. It is physics looked at from the perspective of computer science. So in computer science, or it's a generalization of computer science, to include not just abstract transformations of abstract objects, like numbers, but calculations of them and stuff, but also physical transformations. So like the transformations that occur in factories, assembly lines and stuff. And these 2 very interesting classes of transformation, which are between the concrete and the abstract category. So computations are abstract input, abstract output, and then 2 + 2 = 4. Like physical transformations are like what happens in a factory. Like you take an apple, you get applesauce or something. But preparations and measurements are very interesting because a measurement takes a concrete input and it gives you an abstract output. It gives you like not the whole system. You're just measuring a part of the system. A preparation takes an abstract input, a criterion for how you're going to prepare the system, and it applies it to a concrete system, and you get a concrete output. Now, whether these transformations can be caused to happen or not is a different matter than predicting whether or not they will happen from laws of motion. A transformation being possible doesn't imply that it will happen, because maybe no one will choose to ever in the universe enact the transformation, perform the transformation. And a process happening also doesn't imply that it's a possible, in constructor theory, like process or transformation. Because some processes are the result of quantum fluctuations. They're not able to be caused. Nobody has the ability to cause them. They happen accidentally, and the laws of physics don't allow a machine to be built, a constructor to be built, to cause them, their accidents. So that's yeah. Yeah, so I already said this. A way to think about constructor theory is that it's a theory of not just what abstract computations, what abstract transformations can be performed, but what transformations of any kind can be performed between abstract and physical states or attributes. So that is the way that constructor theory connects computations to the physical systems that they represent. It formalizes the abstract concrete divide And so it formalizes the simulated divide, which the theory of the universal computer does not explain, does not account for. Okay, so now thermodynamics. This is the solution to the problems in thermodynamics. This particular slide is the solution to the problem with the second law, problem with explaining the time asymmetry of the second law that I mentioned before. This is straight from a constructor theory paper, so it's kind of dense, so I'll just read it. Expressing the laws in terms of possible or impossible tasks, not about spontaneous processes happening. Because, like, with quantum fluctuations, bread could untoast. That's a possible quantum fluctuation, but it's not a possible task. Physics doesn't allow a machine to be constructed that will perform it. It has the ability to perform it. Expressing the laws in terms of possible and impossible tasks, not about spontaneous processes happening, has the significant consequence that the statement of the second law requiring that a certain task be possible, but the task representing the inverse transformation, putting a glass back together and toasting bread, be impossible, does not clash with the time reversal symmetric dynamical laws. Because a task being possible, unlike a process happening, requires a constructor for the task. So to toast bread, you need a microwave. To untoast bread, you need something, but the laws of physics doesn't allow you to build anything that will actually do that. And the time reverse of a process, including, yes, that's what I just said. So there's a logical problem in the prevailing conception with describing the time asymmetry. There's no such logical problem when constructor theory describes the second law of thermodynamics. The second problem in thermodynamics that constructor theory solves is expressing conservation laws in a way that's not weak or misleading. So I already explained that this is how the prevailing conception formulates conservation laws. So one way of formulating a conservation law in the prevailing conception is that for every isolated physical system, a certain quantity never changes. Like, will never change, can be predicted to not change. But since an isolated system never deviates from a particular trajectory, almost all its attributes, namely all deviations from that trajectory, remain unchanged, not just conserved quantities. For instance, the energy of the atoms of an isolated crystal remains unchanged, which is what the law of conservation of energy is supposed to explain, but so does their arrangement, as I said. And only the former invariance is due to a conservation law. Right? What makes the attributes that we call conserved quantities significant is not that they can't change when a system is isolated, but that they cannot be changed whether or not the system is isolated without depleting some external resource. That's the key to formulating conservation laws in constructor theory. So in the prevailing conception, the principle of the conservation of energy alone does not rule out perpetual motion machines, because in the prevailing conception, because the statement of the law of conservation of energy in the prevailing conception doesn't rule out external substrates, finite external substrates being used as infinite sources or sinks of energy. It doesn't rule that out. But physics makes it impossible for that to happen. The prevailing conception can't rule that out, can't express the ruling of that out, the fact that it's impossible in physics. Constructor theory can express that regularity. The statement that every task that would change the overall Q just means the conserved quantity of its substrate, like energy, every task that would change the overall energy, say, of its substrates is impossible, implies that there can't be any external substrates that are infinite sources or sinks of energy, say, that could supply a perpetual motion machine. Probability, the solutions to probability. So constructor theory obviates the need for the concept of probability. There's problems with it in quantum theory, like deep fundamental problems. Like the notion of a probability of a measurement of a quantum system violates one of the three axioms of what a probability is. It's not a probability. Constructor theory explains the fact that quantum systems are often mixed and their measurements can't be predicted by introducing some notions. They include the notion of rational game playing. And they exactly define that as the task which is done by a constructor that can't be beaten at a game of basically like Yahtzee. I don't actually know how to play Yahtzee, but the game is like you measure a quantum system and you try to get you bet on the measurements and you try to get the most money. That's not Yahtzee.
I don't remember that being on Yahtzee.
Yeah, me neither. I've never played it in my life. So, whoops. But yeah, that notion can explain how decisions about mixed quantum systems can be made rationally, even without referring to probabilities, without trying to describe the mix of the quantum states in terms of probability. It introduces a notion that's more general than a probability distribution called an X-partition of unity. So it just means the partition of values that you get by measuring X that sum to 1 and obey a few more axioms of probability, not all of them. But yes, this they prove that an X-partition of unity describes a real physical property of a quantum system, and those systems, therefore, they prove that therefore those systems instantiate superinformation variables, or that the properties of superinformation variables are consistent with these properties. And a superinformation variable is a type of information variable that was formalized in constructor theory and of which quantum information is an instance. Now that's interesting because the quantum information was never properly defined before constructor theory. It's a very tough problem to actually define quantum information, and constructor theory defines it as a special case of superinformation. Superinformation is kind of like, if you've heard of the word superposition, having many positions, superinformation is like having many different information attributes at once. So like a state can be mixed, a cat can be alive and dead. Can be alive in one universe, dead in another universe. Bayesianism, the problems with Bayesianism are addressed by constructor theory by introducing a scientific methodology that doesn't rely on probabilities at all. Instead of using Bayesian credences to track how a person is updating how they deal with theories, the notion of a problem, which Karl Popper used in describing his scientific methodology and his epistemology, is formalized in constructor theory in terms of three conditions, which are constructor theoretic. A theory has a problem if it's in conflict with another theory, if it can explain anything. And if the theory can explain anything, then it explains nothing. It's a general purpose excuse for not thinking about an scheme. And The third condition for having a problem, for a theory having a problem, is that the theory doesn't seem to be able to account for certain explicanda. So that's a constructor theoretic definition because it refers to the ability of information to do something, to explain a set of explicanda. And the way we deal with theories using this methodology is that we discard theories that are refuted. And the definition of refutation is that one theory has strictly more problems, a strict superset of the problems of another theory. If another theory exists that is a subset, the first theory is refuted and we discard it, and that is using the methodology. And there are no probabilities in there, so it avoids the problems with Bayesianism. So that's how constructor theory solves all those big problems. And the constructor theoretic, the problems that I want to talk about potentially being solved by constructor theory, and I think maybe an extension of constructor theory, those problems are hard to describe, and it's hard to describe, I don't even know if it's the case, that the prevailing conception is responsible for those problems. So I'll just explain the reach of this theory, its extra benefits. So emergentism is a paradigm in at least consciousness studies that tries to explain consciousness by saying it emerges from lower level phenomena. It's an emergent phenomenon. It's a higher level phenomenon. And then the problem is, like, how do you define that? What is an emergent phenomenon? What is emergence? And one author in particular has come to the forefront of the emergentist paradigm. And his name is Terence Deacon, and he wrote a book called Incomplete Nature. And that book lays out an extension of the field of thermodynamics to explain emergent phenomena in a sort of proto-mathematical language. So he uses thermodynamics to try and formalize the notion of an emergent phenomenon. And near the end of, or actually this is near the beginning of this book, he says something very unknowingly supportive of constructor theory. I'm pretty sure he doesn't know about this, about constructor theory, but near the end of his book he says something. But this is near the beginning of this book. I'll read it. It would be useful to distinguish between changes that have to be forced to occur through extrinsic intervention, physical changes to a physical system, and those that require intervention to prevent them from occurring. So those that happen naturally versus those that must be forced to occur. Surprisingly, there are no terms that characterize this difference. False, that's false. I don't know if I think he wrote his book a year before the first constructor theory paper was published, but constructor theory basically has terms for this. And I have not seen anyone say this. So in order to facilitate the discussion of how they contribute to the range of dynamic processes we will encounter in the effort to explain emergent phenomena, I offer two neologisms. I will call changes in the state of a system that are consistent with the spontaneous natural tendency to change irrespective of external interference orthograde changes. So it's natural, changes that naturally happen in an environment. In contrast, I will call changes in the state of a system that must be extrinsically forced because they run counter to orthograde tendencies, contributed changes. So those must be figured out. People, constructors, have to figure out how to perform them. There are terms for this. In the constructor theory of thermodynamics, a thermodynamic attribute is one that must, once it's instantiated, once a physical medium has a thermodynamic variable instantiated in some attribute, or has a variable instantiated in a thermodynamic attribute, it must then be forced to change if it's to change. It won't naturally change. That's what a thermodynamic attribute is. Therefore, orthograde changes can be called, in constructor theory, transformations away from non-thermodynamic attributes to thermodynamic attributes. So it's kind of like the notion of like a system going into equilibrium from first being out of equilibrium. But it's different than that notion, because the formal notion of equilibrium is in the prevailing conception, stated in that is expressed by the prevailing conception. And contragrade changes are changes from thermodynamic attributes to non-thermodynamic attributes. That's the definition of a thermodynamic attribute, is that changing it from what it is requires force, requires like external influence. And contragrade change is external influence. It's change caused by force. Okay. So here is really speculative stuff. And I presented constructor theory in the way I did because I think it's the best way to understand constructor theory, but also because it makes this leap, I think, more natural. It's easier for me to show why I want this field to be created. So just like the growth of entropy is time reversal asymmetric. It grows as time increases. Yeah. And then but it doesn't grow as time decreases. Understanding, I think there's an analogous law in the phenomenon of understanding itself, in the phenomenon of explanation. And it has to do with which explanations are interesting and which ones are boring for a person to create. Which knowledge is boring to create, which knowledge is interesting to create for a person. And a person is a formalizable, David Deutsch has formalized the notion of a person as being an object which can explain anything. So there's kind of that's not an informal Achilles heel of this field. It would be a formalizable notion, the notion of person. The growth of understanding, is emergence-level asymmetric, I think. Once we've reached a certain level of emergence, let me just make sure I didn't miss a slide. Yeah. I have to explain this first. In constructor theory, emergent phenomena can be formally exactly described, as phenomena which can be explained without reference to the underlying laws. So it's phenomena for which there are underlying underlying systems which kind of instantiate them, to which we don't need to refer, to which we don't need to refer in order to explain what's happening at the higher level. And that's a constructor theoretic statement. So the notion of transcendence, I think, is formalizable. It's like the notion of climbing the ladder of emergence. Once you transcend the problems of your particular situation, your parochial problems, then you reach a higher level of emergence. And once you explain your parochial problems in a way that allows you to solve them, then you don't need to. This is a phenomenon that we see in life. It's like a data point that I'm trying to explain. In life, once we've solved the problem, it's boring to repeatedly solve it again. It's only fun the first time. It's only interesting the first time you hear an explanation. And that jump to creating a new explanation is reaching a higher level of emergence, because once you have an explanation, you don't need to refer to the underlying problems, again, in order to or just simply, you don't need to refer to the underlying problems again. That's a fact about life. That's a data point that I think is a moral, is a data point of moral philosophy that needs to be explained. And I think that the emergence level asymmetry of the growth of understanding is a formalization of that data point that an extension of constructor theory can explain. Because constructor theory explains the time asymmetry of the growth of entropy. And the prevailing conception can't explain that. And there seems to be a gap in constructor theory. There seem to be properties of constructor theory that are similar to properties of the prevailing conception that show that there's like a gap. There's a new theory that could be kind of created, just like constructor theory was created to solve problems that the prevailing conception can solve. I think that a new theory can be created to solve analogous problems that constructor theory can't solve. So this here are a few such problems that are analogous to what I said in the beginning about the prevailing conception. An explanation is only interesting the first time it's created. Let me just read this slide to get kind of back on track with how I structured this. I think that this law of morality, that this data point about life, that things are interesting the first time, and then once you have to do them automatically, once you know them, they're boring. I think it's analogous to the second law of thermodynamics in the prevailing conception. And it's not expressible in constructor theory, right? Because a universal constructor, just like how a universal computer can't explain, or just how a universal computer can compute the forward and backward of burning toast and then untoasting it. Constructor theory can't explain like burning toast and untoasting it are perfectly good computations, and that's why the prevailing conception can't explain the second law, the time asymmetry of the second law. Explaining something and then explaining it again are both possible transformations. And so a universal constructor can perform both of them, just like a universal computer can compute the burning of the toast and untoasting it. Therefore, I think we need to think of a new universal object, and I think that universal object is the notion of a person, of a universal explainer, that David Deutsch has already posited to exist. But I think it is to the universal constructor what the universal constructor is to the universal computer. So yeah, a deeper language could say that for every good new explanation of some explicanda, there's a bad explanation, a boring one. It's not new, and it uses already created knowledge to automatically produce a seeming account of the explicanda, which is designed to suppress curiosity, and it's an account which can't be used to make progress, as argued by David Deutsch in his book, The Beginning of Infinity. And that's analogous to how constructor theory, in the constructor theory of thermodynamics, posits that there's a class of media called physical media called heat media, which can't do work, unlike work media can. Those are some details of the constructor theory of thermodynamics. So there's an analogy between the constructor theory of thermodynamics details and some details that we could say about this deeper theory, about interestingness and boringness. And those bad accounts can't be proven to be worse than a good account. So irrational explanations can't be proven inconsistent with the explicanda. That follows from the Dewey-Quine thesis. And that, I think, is analogous to the fact that in constructor theory, this is a feature of the constructor theory of thermodynamics. It's analogous to the fact that attributes of heat variables can't be measured to be different from or distinguished from other thermodynamic attributes. So you can't prove that a bad explanation is better than a good one. You can't distinguish a heat variable from any other thermodynamic variable. So I think that the distinction between possible and impossible, there's a deeper distinction, maybe needed versus unneeded. And just like can implies will happen somewhere in the multiverse, ought, so needed, implies can in moral philosophy. That's like a common slogan in moral philosophy. People say ought implies can. It has some long name that I can't remember. But possible doesn't imply needed, just like will happen doesn't imply can happen. I already said this. A universal constructor doesn't contain all the diversity of reality, because boring and interesting tasks are both possible, but they don't both need to be performed by any person. The theory of the universal computer ignores the hardware underlying computations and which physical states computations correspond to, and the theory of the universal constructor ignores the problems underlying people's actions and which problems a particular instance of conjecture solves. So that's another similarity with the problems with the prevailing conception. Problem with the idea that the universal computer contains the whole diversity of physics. Okay, this is the last slide. So I think maybe this could be a way to make progress on the binding problem of consciousness too, which is the problem of like, why are phenomenal objects phenomenally bound together? Why is it that I don't see blueness and then like a wall like separate? I see them in one object. That's the binding problem of consciousness. And the problem of other minds is like, why do other minds exist? Why aren't I all the minds? Why am I the only mind that I experience? How do I explain the fact that there are other minds that are not the one I experience? I think it might be able to solve these problems because many possible outcomes of one measurement give rise to many universes, and there's a similarity between that feature of constructor theory and this feature, potential feature of this potential theory, that many problems can be solved by creating one explanation. And those many problems would be instantiated in many minds. So just like there are many universes, this sounds super new agey now, but like, it has like a way of thinking about it from a theory of computation perspective. Also, the appearance of universes is due to the principle of consistency of successive measurements. So the fact that we don't like measure one variable and get a mixed variable and get all different values of the mixed variable, we measure a variable and then it kind of stays with us in our universe. That's a feature of quantum theory that has to be explained. Constructor theory explains it by positing the principle of successive measurements. There could be a principle, it seems like a true principle, the principle of the consistency of problem solutions. Once a problem is solved for one person, it remains solved for that same person. That's of similar structure to the um, consistency of successive measurements, and it might explain the binding of consciousness, just like the principle of consistency of successive measurements explains the unity of universes and the appearance of unified sectors of the multiverse. And two more similarities between this and the second law of thermodynamics, the problem that the second law poses for the prevailing conception, are that higher entropy can be interpreted as a higher degree of branching in the multiverse, and as entropy grows, universes differentiate, and as understanding grows, people might differentiate. I don't know. That's a conjecture. But there might be some regularity there that can be explained by theory that has that kind of structure. And this solution relies on a phenomenon that seems closely related to quantum coherence, and quantum coherence is closely related to, because quantum coherence is closely related to thermodynamics. And quantum coherence has been suggested by a few people at Oxford as a potential explanation of the binding problem. So it connects to already existing explanations of the binding problem of consciousness. That's the whole talk. I'm done. Should I keep recording for questions? Yeah.
So I'm still fuzzy about how constructor theory is used to explain physical phenomena. So for something like the acceleration of an object, the force divided by the mass is the acceleration. What does how are its theorems or statements formed?
Well, there is no constructor theory of space-time yet. So there's no constructor theory of motion yet. But the flow of energy from potential energy to kinetic energy in the form of acceleration is an instance of the flow of information, because all work variables in the constructor theory of thermodynamics are information variables, and work variables are variables which have equally spaced values in a conserved quantity, like energy. The constructor theory of thermodynamics goes some way to explain some of the aspects of accelerating objects, but there's no constructor theory space time yet.
Is constructor theory related to quantum gravity, or are they?
Well, both are potential theories of quantum gravity. Well, root quantum gravity is a theory of quantum gravity. There is one quantum gravity result from constructor theory that's very interesting. It is a proof that gravity must be quantized in constructor theory. Proof from using principles from the constructor theory of information. That's a pretty significant proof, I think. I don't think anybody's ever. Feynman argued that, but there were some objections that hadn't been addressed until constructor theory addressed them. Yes, gravity must be quantized because, like, entangled pairs must mean that it must be possible for quantum systems to be entangled with classical ones, and I think then the classical ones obtain quantization by that entanglement. I think that's the argument. It's tough. It's a short paper, but it's pretty conceptual. It's the newest paper.
So I'm unclear on how you're going from thermodynamic properties of quantum interactions to things like whether something's interesting or boring. It seems like there's many levels of abstraction that you're.
Yeah.
over there. So
I know. Well,
how are you getting from thermodynamics of quantum interactions to interesting and boring?
Well, yeah, I tried to lay out some of the structural similarities, but like, okay, it's not intuitive that like morality, the field of morality, would be like one level deeper than it would be like morality is to constructor theory as constructor theory is to the prevailing conception. Yeah, that's not intuitive, but for 7 years, I was trying to like explain morality in terms of physics, and that's why I got interested in constructor theory. And so I'm a little more warm towards the idea, but it could be wrong. It's crazy. Uh, I haven't received much criticism of it, so there's definitely tons of flaws in it. I don't even know how to formalize it. Um, but there's a lot of structural similarities. Like there's a natural dichotomy, just as there's a natural dichotomy in constructor theory between possible and impossible. The needed versus unneeded dichotomy is very is just as simple. Also, David Deutsch in his tweets and his books uses the word needed a lot and unneeded. He uses that dichotomy a lot. So part of this is like me trying to figure out where David Deutsch is going, that he's not publishing his thoughts. And part of it is like I just am super interested in morality and ethics, and I've always tried to think about ways of formalizing moral theories. Yeah, so that's a little more explanation. Go ahead.
Are you familiar with the story of Ramanujan, where he says there's no uninteresting numbers?
Oh, right, the argument that there's no uninteresting number because like if the smallest uninteresting one is interesting because of that reason.
Right. So I'm just wondering, like, how can there be quantum interactions that are boring?
Oh, well, I mean, that's just an argument that no number. Well, see, like, okay, what if you? I mean, if you keep doing that process, like, oh, this is the smallest boring number, smallest uninteresting number. That's interesting. And then you keep doing that. That's boring. I think. I don't think you can actually do that process. I think maybe the argument fails.
It's a process that's boring, not so much individual entities. It's just once you go through the process of eliminating all the interesting numbers, at a certain point you see that there's a mechanism for generating them, and there's no point in continuing to do it.
Well, that is a good counter argument. Yeah. Well, but certain things. I mean, certain things. So would you say that like if you've been working at a ice cream factory for 10 years, that it's still interesting? That seems like naturally more boring than like what I'm doing with this theory. Like, I'd rather try and work out what I mean by this, or what the potential of this theory is, than do ice cream cones for 10 years. It seems to me like a feature of the world, the distinction between boring and interesting ideas. And it seems to me actually to be the fundamental moral distinction. And David Deutsch convinced me of that. I used to think it was like pleasure versus pain. I was a utilitarian for 7 years. But David Deutsch's epistemology connects to morality in a very powerful way. And interesting and boring are fundamental epistemological properties. You still seem totally pained at what I'm saying.
Yeah.
Can it interesting and boring be quantified in some way relative to information theory?
That's a good
Not
I-
adding information.
I don't know that interesting. David Deutsch has said that he doubts that there's a natural measure on the space of possible transformations. And an explanation is a transformation, I think, of a information attribute. It's like a mutation of old knowledge to form a new idea, just like genes are mutated to form a mutation. A new gene, a new explanation that gets created is a mutation. It's a permutation from one information attribute of an information variable that is part of an old explanation to a new attribute, and that makes the new explanation new. So it's a transformation. I forget what your question is.
Just can you quantify it using Shannon information theory or some way to say this theorem is interesting because it adds information to our understanding of the universe or something?
I think it might be like a binary property, like interesting or boring. Because it seems like things are interesting for not because they are in a way that we don't understand before we've like found the idea. Like because like the interestingness of general relativity to Einstein wasn't that he had some measure for theories and was like, oh, how do I get a theory this high on the measure? And then like deduced from that value what general relativity was. And nor was it the case that, okay, you might say like he had like a certain number of calories of energy added to his brain when he was so like excited by this new theory. That would be a way of quantifying some results of the theory. But the interestingness of the theory seems to me to be due to not a thing that can be measured by one apparatus, but it seems to me to be due to features of each interesting object. It seems to me to be like particular. The reasons things are interesting are different in every situation. So different things are interesting for different people. Like general relativity isn't interesting to people today who already know general relativity. So different things are interesting to different people. So that doesn't like imply that you're wrong. I don't think I said anything that actually logically argues against what you said, or argues against the notion of a measure. But I find that research project of trying to define a measure on explanations in terms of their interestingness to be uninteresting and to be not promising, because I don't see a way of doing it. It is what utilitarianism would suggest, but not a utilitarian.
It almost sounds like you could dumb that down to a point where it's interesting when it's new and novel, then you determine its relevance going forward.
Right.
So if it becomes an important building block, it's not interesting. It's almost like a third category where it's relevant. If something is not relevant, it's automatically boring.
Yes.
Because it's not a building block. But we have a connotation in our own mind that something is interesting if it's relevant. But if it's interesting and we prove that it's relevant, it really isn't interesting anymore, because you said earlier you kind of discard it because there's no reason to go and revisit it.
Exactly, right.
It's just an established building block. Yeah.
Right.
And so
I
guess you could call it significant and relevant.
I agree.
But it's not interesting anymore.
Yeah.
Observation on that. It sounds like relevant is synonymous with need.
Yeah.
I agree
Oh, yeah.
with that.
Absolutely.
That's kind of a better exposition than I was going to respond to. Yeah. That seems to be. I agree with what you're saying. Like the David Deutsch's thoughts on this, which I pretty much agree with, are that like bad explanations are those that use old knowledge to excuse thinking about a problem. Like religious explanations, like I imagine like a strict like religious teacher, like just you ask a question about physics and they're like God did it, their characteristic property is that they squash curiosity. They use old knowledge as a general purpose solution for, not really a solution, but like as a general purpose excuse for not thinking. So yeah, when an idea is not new anymore, when you've already drawn out all its implications, and done all the experiments, then it's not new anymore. I think that's what you're saying. Right? I think, yeah, that's a good thought.
So you're trying to link this to morality.
Yes.
So is it morally wrong to bore people?
Did I bore people with my ums and pauses?
No, I'm asking a
Yes.
morality question.
Yes, it's morally wrong to bore people. I think so. Yeah, that's super. Like, I don't want to be bored.
Okay. I don't know how you get this from physics.
Thank you all for
Yeah. Stop this recording. I'm pretty sure it didn't record like my face at all.